In this around 10 minutes talk, I'd like to support your understanding for applying final value theorem and initial value theorem, especially final value theorem of characteristics of Laplace transformation to be applied by application of like type 1 PLL error transfer function response, like written in page 663 of Razavi textbook, example 16.5. So what's a final value and initial value theorem? A final value means when t approaches 0, infinity, t approaches infinity, how we can derive the f of infinity from applying Laplace transformation, which is simply s times f of s, where f of s is integral with respect to t from 0 to infinity of ft times e to the minus st dts is j omega where here, or sigma plus j omega and sigma positive usually, and fs, and likewise t approaches 0 from the positive value plus 0 plus f 0 plus can be derived via s approaching infinity of f of s. We need to remember this, but it's easy to remember of this. No, what I should say? Symmetricity, non-symmetrical, inverse symmetrical form. T approaches infinity, s approaches 0, t approaches 0 from positive value, s approaches infinity. And then deriving this is very roughly needs just this one. Which is dft dt. Taking a limit of s to 0 makes this this is unconditionally just keeping minus 0 plus, and this is limitation inside about s approaching 0 in this case, while t approaches infinity, but both sides going to like this, and this approach is just 1 for while s0 yields 0 equal 1. Roughly speaking, it's 1. So this is df dt makes just ft from 0 to infinity makes f infinity minus f0. F0 cancelled out, and we can so this is the final value. And initial value is likewise utilizing this formula and take the limit of s infinity, while s going to infinity of f times f of s minus f0 plus equals, if s infinity, these parts on the other hand going to 0. So this is 0. Then we can get this formula. Next application of this final value theorem, it's useful, and we need to remember this formula. And error transfer function is about the phase P in to P out. And this one is P in S, P out S, and H of S is actually omega out S divided omega in S equals omega equal d phi dt. D dt is linear operator. So this is equal, and we know that this is both are equal omega natural frequency squared divided by s squared plus damping factor zeta times omega sub n s plus omega sub n squared. This is h of s, and the phase error is defined p in minus p out, and its transfer function is divided by phi in, which is 1 minus h of s from here, and it is just 1 this divided by this minus omega sub n makes s squared plus 2 zeta blah blah blah. And this is written E sub E of s, error transform function of phase or omega, and this time phase. Is in this example of 16.5, if at time t equals 0, delta omega is applied for some reason, then what is the final stabilized phase shift after this application? And this is about omega, and this is about phase. So we need to change this to phase step. For utilization of Laplace formula, S space, we need to get delta omega as a Laplace transformation style, F step S space. While d omega equal del theta del t d theta. If neglecting other variation of parameter concerning relative to relevant to omega, neglectable, we can concentrate on this. And sorry, this is dt. The omega d omega dt d del omega dt. Just time difference. Considering just time variation, we know this, and integrate of this makes omega simply d omega after integration makes omega, and we need phase phi, but integration with phi with omega is makes phi because omega is del phi del t. So del phi dt del t. So integrating del phi del t dt makes phi. So, and the integration as a transformation, Laplace transformation, just multiplying 1 over s. So multiply 1 over s twice makes phi of s input. So we need to know just h sub e of s times phi sub in of s is phi sub out of s, and which is, this is delta omega over s squared. So s squared cancelled out, and 2 zeta omega sub n divided by s, all over divided by s squared plus 2 zeta omega n s plus omega sub n squared. And applying this final value theorem, we can derive when t going to infinity, stabilized value of phi is what? It is just from this theory, s times phi out s approaches 0, which is s plus 2 zeta omega sub n divided by s squared 2 zeta omega sub n s plus omega n squared. And this s approaches 0. This is 0, 0, 0, and which is 2 zeta omega sub n divided by omega sub n squared, and squared cancelled out, 2 zeta over omega sub n, which is sorry, s squared S times phi in S squared 1 over S squared times delta omega. S times delta omega which is delta omega over KPD times KBCO. Please check 2 zeta over omega sub n is 1 over KPD, KBCO. Likewise, we can apply final value theorem to derive the stabilized value of the response, phase response